Hello students, good morning. My name is Dr. Mallikarjun, working in Institute of Aeronautical Engineering in the Department of Information Technology as a professor. I am working. So I am giving the series of video lectures of the course of operating systems. Today I am giving the complete explanation of the topic paging. Paging comes from the memory management techniques. So last videos I explained the different scheduling algorithms, how the scheduling algorithms works managed by the CPU. In this paging comes under the part of memory. So to manage the memory and discuss the memory part of view, we will discuss the completely paging. Paging in the context of operating systems is a memory management technique. This memory management techniques allows that once process is going to switch in the memory, that memory is working in the static nature or dynamic nature. Means that memory have access the memory more efficiently based on physically available of the memory portion. The memory have two parts. One is that primary memory and secondary memory. So here we discussing the mainly focus on the primary memory. Means that if the process entirely works and the process running, everything goes on the primary memory. Once process is saved, that is going to be the secondary memory. So entire discussion of the memory management techniques comes under the primary memory or main memory. So primary memory or main memory both are same. In actually physically available by portion of hard drive as that virtual memory, that's discussing of the paging. The paging involves that dividing the both virtual and physical memory into the fixed size of blocks. Divide the memory into the fixed size of the blocks called as the pages and frames. Okay, there is a main memory. In this main memory, we divide into the main memory into different size of partitions. Then we call it as the pages or frames. There is a slight difference between pages and frames. Pages are different and frames are different. So that pages and frames respectively, the swapping these pages between RAM and the hard drive as it should be mainly needed. That pages and frames are two complete different topics. Let me discuss the paging in detail. In the operating system, paging is a storage mechanism. So why you are dividing the memory into different partitions means that that information is stored in the pages. It is a storage mechanism used to retrieve the process from secondary storage into the main memory. That secondary storage information that completely switch to the main memory. That portion of the memory into the main memory in the form of pages. Actually, that memory has been divided into different partitions, means that those are called as the pages and frames. These partitions was used to store the information. This information can be processed from secondary storage into the main memory. So this information this is main memory, and one more side it's there in the secondary memory. This the stored information is going to stored in the secondary memory permanently. The information which is stored in the primary memory, that is going to sit in the secondary memory permanently. The information is stored in the secondary memory, because once the stored information in secondary memory means that it can't be erasable further once the user wants to delete. So that the main idea behind the paging is to divide each process in the form of pages. The process can be divided. Here in the memory there is a process P1. That process P1 keeps on going to divide into different number of pages. The main memory will also be divided in the form of frames. One page of the process is to be stored in the one of the frames of the memory. One page and one frame, one page of the process is stored in the one frame of the memory. Every page is nothing but one frame of the memory. So pages and frames are two different partitions. Both are same. In the main memory is divided into different partitions or pages. The secondary memory is divided into different partitions or called as the frames. Okay. Pages of the process are brought into the main memory only when they are required. That which process has required that partition of the memory, that can be switched from the secondary memory to the main memory. That can switch means that information is swapped out from the main memory. When that secondary memory requires the information, then secondary memory needs that information is swapped from that again main memory to secondary memory. This is called swap in. Okay, let me discuss swap in and swap out in another lecture. But now we are going to discuss about the paging process detailedly. Different operating systems define different frame sizes that depend upon the memory size, total memory size. Some hard disks have 540 TB, 1 TB hard disk. We seen 500 GB hard disk. We see that each size of the hard depends upon the paging and framing, depends on the size of the hard disk. The size of each frame must be the equal. Consider the fact that the pages are mapped to the frames because of the concept of the paging. Page size needs to be as the frame size. Both should be the equal, then only the paging technique should perform. Page size and frame size should be the equal. The page size needs to be as the frame size. Here, there is a mapping from the main memory is divided into the number of partitions are called the frames. This is the main memory. The main memory divided into number of partitions we called as the frames. Let me take as the secondary memory divided into the number of partitions are called the pages. So let me take in process of paging from the secondary memory. The pages can be mapped to the primary memory or become as the frames. There are 9 pages once you've seen in the secondary memory. Page 1, page 2, page 3, page 4, so on up to page 9. There are 9 pages are there in the secondary memory that can map it into the primary memory. It becomes as a frames. That become page 1 become frame 1, page 2 become frame 2, page 3 become frame 3, page 4 become frame 4, page 5 become frame 5, page 6 become frame 6, page 7 become frame 7, page 8 become frame 8, page 9 become frame 9 as individually. So this is called mapping. Mapping from secondary memory to primary memory. The pages which are mapping is called mapping technique. It's a page mapping technique or process of paging. The process of paging from secondary memory to primary memory is called mapping. This is a one process P1. Let me take in the secondary memory, that can be mapping that each page into the in the primary memory is become the framing. So this is in the primary memory concept is called framing. In the secondary memory concept is called paging. Then those two are mapping takes place in between secondary memory to the main memory is called paging technique. Okay, this is called page map table. That is a table. There is a frame table and this is a page table. This is called mapping, is called page map table. That is a page map table. Then let me see one example. Let us consider the main memory size 16 KB. Let us consider the main memory as the 16 KB. This is a main memory. This the entire size is 16 KB. And frame size is divided into each memory as frame size is 1 KB, and dividing each frame size is 1 KB, 1 KB, 1 KB. Therefore, main memory will be divided into the main memory is divided into the collection of 16 frames of 16 divided into 1, 1, 1, totally collection of 16 frames each. So 1 KB, 1 KB, 1 KB, totally 16 partitions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 partitions totally. I am going to divide the main memory. So each partition is 1 KB. So there are four process. This is process P1. This is process P2. This is process P3. This is process P4. So P1 process, P2 process, P3 process and P4 process. There are four process P1, P2, P3 and P4. So each process have 4 KB each. This process is 4 KB. 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 4 KB each. So each process is dividing into the pages of 1 KB each. So each process P1 has 1 KB. P2 has 1 KB, P3 has 1 KB, P4 has 1 KB each. So that each process 1 KB each is stored in the one frame. This is as a one frame, this become as one frame, this become as one frame, this become as a one frame. These frames are empty, therefore pages of the process will get stored in the contiguous way. This contiguous way of allocation, here giving the example. Let me see the complete detailed diagram of the process P1, P2, P3, P4. It divided into 16 KB of the process P1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There is a 16 KB of the memory divided into the partitions. So each partition has got the 1 KB. One frame actually in the main memory is a collection of frames. So these frames, there is a process P1 has a 4, 1, 2, 3, 4. Therefore P1, P2 has 4, 1, 2, 3, 4. P3 has 4, 1, 2, 3, 4. P4 has 4, 1, 2, 3, 4. 4 frames individually. So P1 is mapping to the main memory. P2 is mapping to the main memory. P3 is mapping. P4 is mapping. This is a detailed representation of paging of each process, that is map. P1 is mapping to the each process into the main memory. P2 is mapping each process into the main memory. P3 is mapping each process into the main memory. P4 is mapping each process into main memory. P1, P2, P3, P4 all are matching individually, completely individually. This become as a completely page map table. In this completely detailed representation of paging concept has been observed in this slide. We observed that P1 is mapping completely, P2 is mapping completely, P3 is mapping completely, P4 is mapping completely, all mapping in the main memory as a 16 KB. All are become as the collection of frames. So each frame has become a 1 KB each. That frame size should be the equal as the page size. Frame size and page size should be the equal. Then only the mapping technique take place because frame size and page size should be the equal. Because each process have 4 KB, 4 KB, 4 KB. There are 4 process. Each process has 4 KB. Total main memory is 16 KB. So it is completely frame size and page size should be equal. Because total process size is 16 KB. Total main memory become as a 16 KB. It is individually mapping. The frame size should be equal as the page size. Okay. Let us consider that P2 and P4 are removed and they are become as the waiting stage. So let me remove the P2 and P4, those going to be waiting stage. Now 8 frames become as an empty and therefore other process that can be loaded into the empty place. That process P5 that process size is 8 KB of the pages. That is waiting inside the ready queue, that 8 KB of size of the process. Given the fact that we observed that 8 is non-contiguous frames of 8 size of the 8 KB of the size of the process available in the main memory, and paging provides the flexibility of storage of the process at different places. Therefore, that we can load that pages from process P5 in the place of process P2 and P4. This is the one example. In the previous slide, there is one more process P5 that is 8. That process size is 8. 1, 2, 3, 4, 5, 6, 7, 8. There is 8, totally 8. Now is removed from P2 and removed from P4, where we can store this process P5. Become process P2 is in waiting state, it goes. Process P4 it goes to waiting stage. Then process P5 can occupy completely P2 4 bits, first 4 bits are occupied, P2 first 4 bits are occupied, next 4 bits are occupied in P5. That is the procedure. So that process can completely removed. Then P5 comes. Then that P5 completely occupied that. P5 completely occupied that process. So that is that 8 pages of the P5 is came. That should be wait for the P5. Then P2, P4 are removed. Completely P5 comes, that can be occupied instead of the process stages from P2 and P4. Okay, that structure of the page table simply defines that in how many ways the page table can be structured. The paging is a memory management technique where large process is divided into pages and is placed in the physical memory, which is also divided into the pages into the frames. The frame size and page size should be the same and both are equal. The operating system uses a page table to map the logical address of the page generated by the CPU to its physical address. In the main memory, there is a logical address and physical address. That we will discuss detail later. That operating system uses that is the information of page table that defines that differently. Logical address is different and physical address is different. That is the memory management technique. That is logical address and physical address. There is a mapping between the logical address to the physical address. That video I will give that video in my next lecture. So the page table structure having 3 methods of the logical address. That is hierarchical paging, hashed paging, and inverted paging. Hierarchical paging comes under 2-level paging, 3-level paging, and 4-level paging. That gives to the hierarchical paging. But hashed page table is completely different than the hierarchical paging. Let's see the two-level paging procedure. So every paging technique, there is two things. One is the page number, another one is the offset. This is the address of the page. So paging having two techniques. This is the paging. This is the paging. Divide the memory into different slides of sort. Each slides have one is page number, another one is the offset address. One is the page number, another one is the offset address. Page number we can represent it as the P. Offset address we represent it as the F. Page number we represent it as the P. Offset address represented as the F. Page number we represent the size of the address is 20. Offset address we represent as the 12. Then page number we represent as the 20. Offset address we represent as the 12. As the offset address we represent as the D. Offset or page size. Page number, every page having page number and page size. That is the information for every page. Let me see the structure of the page of the hierarchical paging. See, hierarchical paging, first you see the two-level paging. Two-level paging to store 1 million entries in each page. 1 million entries in each page in the two-level hierarchical paging. Now this entire page table must be stored in the main memory. Entire page table must be stored in the main memory. The access of main memory, it requires more amount of time. How to access the memory? That is required more amount of time to access the main memory. To overcome this problem, instead of storing entire page table information in one page table, we divide this information into multiple page tables. Let me take the logical address. That logical address having P1 and P2 and offset. There is a logical address. That logical address have divided into three partitions. That is page 1, page 2 and offset address. Page 1 is the outer page table. Page 2 is the inner page table. And D is the offset of the physical memory. This structure is called as a two-level hierarchical page table because a page table having divided into P1 and P2 and offset. P1 gives the outer page table, P2 gives the inner page table. It requires that outer page table and inner page table memory requires that more amount of time required for the outer page table and more amount of time required for the inner page table. That is the storing entire page table information from one page table to another page table. Divide the information into the multiple of the page tables of the two-level hierarchy of the page table. Okay, let me discuss in detail of the two-level page table. Let us discuss the two-level paging in which page table itself is paged. So, we'll have two-level page table, inner page table and outer page table. We give the logical address with the page number as 20 and offset address is 12. As we are paging a page table, the page number will further get split into 10-bit page number and 10-bit offset number. Here, P1 would act as index, P2 would act as a offset for the outer page table. P2 would be the act of index of D, would act as the offset of the inner page table. So P1 gives to the outer page table offset page number, P2 gives the inner page table of the page number. Offset is the common for both outer page table and the inner page table. Offset is common. Let me that inner page table to map the logical address of the page, that is the physical memory. So this is the way of the hierarchical of the page table. This is the two-level page table. It similarly goes to the three-level hierarchy of the page table. There is a P1, P2, P3 and offset is there. Then P4 having P1, P2, P3, P4 and offset is there for a four-level hierarchy of the page table. So this is the way of the hierarchical of the page table. Page number and page offset should be clarified by the two-level hierarchy of the page table and the three-level hierarchy of the page table and four-level hierarchy of the page table and keeps on. All processes are going to be working with the these level categories. Okay, similarly, the outer page table, how it works, the inner page table, how it works, that is depend, that can be mapping with the pages with the offset. Okay, then similarly, we can see the 3-level hierarchy of the paging also. Okay, next, hashing page table. So there is a hash address. The page table is mapping because of the hash address. If hash address is should be matched, that corresponding page should be active. When the logical address space is beyond 32 bits, in such case that the page table structured using to hashed and mapping with that page table. So we can structure the large page table using the multi-level page table. It would consist of a number of levels increases, the complexity of the page table also increases. The hashing page table is convenient way to structure the page table where logical address space beyond 32 bits. The hash table has several entries where each entry has a mapping with the linked list. There is a linked list having one data structure we studied in detail in the course of the data structure. There is a linked list or single linked list and double linked list. Single linked list, there is a address for every link, every node, there is address and there is a data. So address of the node, there is a node, and this node having one is the address part and one is the data part. That address part is linked to the next node. The next node address part is linked to the next nodes. The same way here, hash page table, that every page having hash index address, that address is linked to the next node, means next page. That address is linked to the next page. Is that form in the linked list manner. That is the linked elements where each element has to some location. Each element has 3 entire page number, frame number and pointer to the next element. So page number and frame number and pointer, that pointer points to the next page. So this is the mapping of the hash page table, because this is also called multi-level paging. The multi-level paging we can't see in the hierarchical page table. The multi-level paging we seen in the hash page table structure. In the multi-level paging we can see in the inverted page table also. See, this is the structure of the hash page table. There is a logical address, page number and offset. That page number and offset refer to the hash function. That hash function is referred to the page number and frame number and pointer address. That pointer address is mapping to the next page in the sequence. The next page number, frame number and offset. That means that is the address. That address is mapping to the next node, that is page and frame and address. Then it mapping to the corresponding frame is mapping to the corresponding node, frame number and offset. That offset is referred to the physical memory. Again, that offset is referred to the logical address. So this is the structure of the paging technique in the hashing table scenario. This is hash page table manner, hash table structure. The hash table structure having the linked list fashion. That linked list having node and address part. That address part is referred to the next node. Keeps on, that is mapping to the logical address and physical address. Coming to the last page table structure, that is inverted page table. Inverted page table is also known as inverted page table or inverted paging, both are same. In the memory management technique used in operating system to map the virtual address to the physical address. Using traditional paging, it is completely different from the inverted page table. Uses a single global page table indexing physical frame number. So, single use number and physical frame number. This approach is reduce the memory overheads. See, memory overheads is too much in the hash page table. See, this hash page table memory address are using maximum address are wasted. There is again we use the address for every page, that is wasting. So we reduce these address spots. We invented this inverted page table to overcome the hash page table process. Inverted page table is invented. This page table for each process, especially in the system with many process, we worked out this inverting page table. This inverted page table having page number, process ID, page number, process ID and offset, that is mapped to the page table. That page table having page number, process ID and control bits. It search for the page number for every slide in the page table. That page size is 2 power n and frame size is also the 2 power n. That should be matched in the page table. That can refer to the address of the physical address I and offset that can match with the physical memory. Physical memory gives the 2 power n frames and page size also gives the 2 power n. That can be mapping in the inverted page table. That address I and offset, that is mapping with the physical address of the physical memory. In that should be formed in the inverted page table. So inverted page table is efficient than the hash page technique and hierarchical page technique is efficient of the inverted page table. So when you compare to the hash page table and inverted page table, the hash addresses are less in the inverted page table. So inverted page table directly mapping with the page number with the page table and with offset is mapping with the physical address occurred at a time in the inverted page table. So that's why inverted page table is efficient compared to the hierarchical page table and hash page table. Students, okay, in this video, information collected from the reference books, Abraham Silbert Scratch Peter B. Ganglin book. The title of the book is Operating System Principles, Wiley Publishers, 8th edition 2010. And also I collected the information of this William Stallings book, author William Stallings. Title of the book Operating Systems, Internals, Design and Principles, Pacer Education Publisher 2002. In this video lecture, I explained completely paging technique in the memory management in the course of operating system. Thank you, students. Thank you for watching this video.
Like, share and subscribe. Hit the bell icon for more updates.